Okay,
Oh, teacher.
these are by previous division of syllabus. Oscillation and waves usually teach together. Under waves, you have topic 7, waves, then 8, superposition, and then oscillation. Oscillation is going to under A2, right? Because it's more mathematical. Okay, just a summary of the topic. The picture form will show you what are the things you're going to cover. Progressive wave, 10.1, 10.2 transverse and longitudinal waves. Then we are going to determine the speed and frequency of the wavelength. And Doppler effect, that's summarized for you. Doppler effect, you can memorize the picture, will help you, very helpful. Electromagnetic spectrum, that's the electromagnetic spectrum. And then polarization, that picture summarized for you what it means by polarization. Okay, that's your syllabus. So under this topic, we will teach cathode ray oscilloscope. Okay, you won't bother about that. Let us go to YouTube. Where is the thing? Where is the thing? Where is the thing? Sorry, I'm just looking for a video to show you. Okay, just listen to the video. If any problem, let me know.
Hello friends.
Teacher, there's no audio. Hello, teacher.
So created in the lake is caused due to the to and fro motion of the water particles. So now in this module, we are going to discuss about the various types of waves. Like in our previous module, we have taken a situation where a group of people were standing in a queue and all of them was holding each other through their shoulders. So what did we observe over there? What was actually happening over there? When one person sits down, he pulls his neighboring person to sit down as well. And when he stands up, he again pulls his neighboring person to stand up. So it keeps on moving that way. So each person here is undergoing only up and down motion. And this disturbance is propagated towards the last person of the group. Similarly, we can take an example of a rope. So if I have a rope with me, you can see here, the disturbance, it travels through the rope. And how this is traveling through the rope? Let's see. What do you see if you carefully observe this rope? Yes, if you carefully observe this rope, then you must have noticed that the red dots, the red dots which are present on the rope, they keep on undergoing to and fro motion about their mean position. While the disturbance, it keeps on traveling forward through the rope. So what do you conclude from the above two examples? So it is concluded that it is the disturbance that is carried forward, but the particles of the medium, they are undergoing to and fro motion only, and that is about their mean position. So here the waves, they move straight from one end to the other end, while the particle motion which makes that particular wave is in a direction which is perpendicular to the direction of propagation of the wave. Now this type of wave is called as, any guesses? Yes, this type of wave is called as the transverse wave, in which the particles of the medium, they move in a direction which is perpendicular to the direction of propagation of wave. And some of the examples of transverse waves are the water waves, which are formed when I drop a stone into a lake or a pond, the light waves and the radio waves. These are all examples of transverse waves. Now let's do a simple activity to demonstrate how a transverse wave looks like. Let's take a slinky and place it on the table, and we are fixing its one end and the other end is let free. Now I hold the free end of the slinky and just whip it. What do we observe? The slinky, it appears to move like a snake, and it shows a wavy appearance. What kind of wave does this vibrating slinky represent here? Yes, we've studied this, and it's a transverse wave. A transverse wave in which the particles undergo to and fro motion about their mean position and moves in a direction which is perpendicular to the direction of wave propagation. Now we'll take the same group of people that we had taken earlier, but this time with a slightly different arrangement, and let's see what happens. So it is the same group of people, but in this case they're not holding each other through their shoulders but through their elbows. Now in this case, the first person, he gently pushes the second person sideways and then pulls him back. You see this push and pull moment, and this is propagated towards the last person of the group. So how is this moment different from the previous one, where each person is holding each other through their shoulders? Now that's something which we have to look forward to. You can see here in the previous case, each person was undergoing up and down motion, while in this case, each person is moving back and forth about their mean position. And the push and pull is transmitted to the person at the end. Now consider the case of a slinky whose one end is fixed to a point. What happens? Now I give a sharp push to it, and what do we observe? Yes, you observe that some sort of disturbance is carried forward from one end of the slinky to the other end. What is this disturbance? This disturbance is carried forward while all the rings of the slinky are moving back and forth about their mean position. But the disturbance, it gets carried forward. Now if I push the slinky forward and backward continuously, then what do you see? It's another interesting thing that we observe. You see here a series of compressions followed by rarefactions, compressions and rarefactions, where the compressions are the regions where the rings are crowded together and rarefactions are the regions where the rings are far apart. So compression and rarefaction both move forward. And in this case, wave motion is in one direction, and the motion of particles of the medium are in a direction which is parallel to the direction of propagation of the wave. Now what do we call this kind of wave? This presents us the second kind of wave, which is known as the longitudinal wave, in which the particles of the medium, they undergo back and forth motion about the mean position, and this is parallel to the direction of propagation of wave. And some of the examples of longitudinal waves are the sound waves. So when I'm speaking, the sound wave which I emit from my mouth is an example of a longitudinal wave. So let's summarize till now whatever we have studied. We've studied that there are two types of waves, a transverse wave and a longitudinal wave. A transverse wave in which the particles of the medium move in one direction, which is perpendicular to the direction of wave propagation, and they oscillate about their mean position, to and fro motion. The examples were a ripple on a pond or a lake and a wave on a string. They can be easily visualized as transverse waves. Some of the other examples that we studied about were the light waves, the heat waves, and radio waves. All are examples of transverse waves. Now coming to the longitudinal waves, the second kind of waves, in which the particles of the medium, they move in a direction which is parallel to the direction of wave propagation. And we had the examples of sound waves, a wave in a slinky. So these are good visualizations of longitudinal waves. So this is all about the types of waves, and in our next module, we'll discuss about sound waves in detail.
Teacher.
Yep.
For transverse wave, the particle move up and down, but the wave moving forward, right?
The wave move forward. The particle stay. The particle is the one oscillating, moving up and down. No?
Oh,
We
how
call it
about
simple harmonic
longitudinal?
motion. No? Okay.
How about longitudinal waves? That one, the
Longitudinal wave,
particle.
the particle oscillate about horizontally, same direction as the propagation of the wave.
So can I say for transverse wave, the particle oscillate vertically, and then the longitudinal
Transverse wave,
oscillate.
the particle oscillates perpendicular to the direction of motion.
Oh yeah.
We will go over lah. I just give you a visual so that you can understand what is happening. We will go over. Anything you can stop me, anything you want to ask.
How about the longitudinal waves? How does it oscillate?
Longitudinal wave is the
Parallel.
same thing. If it's
Parallel to the motion.
parallel to the motion, but the particle doesn't
okay,
move.
okay.
Particle oscillate also like a spring lah. Okay, let us make a start. Can you see the diagram?
Yes.
Okay, let me ask you a question in the cartoon there, just for curiosity lah. Why does the top of the wave curve forward as it moves towards the land? Any idea?
Is it because it's very light? I mean, like, gravity.
As the wave moves towards the land, the wave near the land moves slower than that on the surface, right? Different layer. You can think of it as different layer lah. So the surface one is moving faster. The one near the land is moving slower. So that's why it's curved that way. Anyway, just for your curiosity only lah. Okay, we won't bother about reading that. You can read during your free time. Just summarize to you what we are going to study. Okay, progressive wave. A wave is a periodic disturbance in a medium or in space. Periodic, that means it happens after a certain time lah. Keep on happening after a certain time. The disturbance repeat itself after a certain time. If you look at the bottle, as the wave move along, the bottle doesn't move, but it moves up and down. We call it oscillation or simple harmonic motion. Right? This one shows the blue one moving forward, The red one is the reflected wave. In progressive wave, or sometimes we call it traveling wave, energy is transferred from one place to another. That's how we describe progressive wave. Energy transfer from one point to the other. How do we know? The bottle will move up and down. As the wave passes through the medium, the particles of the medium are in simple harmonic motion. Right? We call it oscillation or simple harmonic motion. You study in A2 in more detail. Each particle is in different phase of motion. Different phase means different position of their motion in the path. We'll introduce the term later on. No particle is permanently at rest. That means as the wave passes through, the particle will either at rest or moving up and down. It doesn't stay at rest permanently. Right? Phase, you can think of it as different position in an oscillation. Water waves. These are water waves. Right? Pulse. When stone is dropped into water, the ripple travels outward. That is called a pulse. You just see only that one, that's all. A shot, not the wave. To have a continuous wave, you have to keep on dropping the stone at certain interval. Then you will see the wave continue flowing. If not, it will just be a pulse. Right? Temporary pulse. Or short waveform. So you can think of your wave as a sine curve. Moving forward like that. A wave moves through the medium, each particle at different phase. Right? The particle there, if you look at this point, the particle is here. After that, as the wave moves forward, when you look at this line, the particle is here initially, then it goes up as the wave moves forward, and then it goes up that way. So it's basically going up and down. Same with other particle. You can look at other particle itself, like here, it's at the top there, right? It's not moving. When it's at the top there, then it goes down, then it goes down further, then it goes to the end there, and then come down forward. Different position of the wave. This particle is at the bottom, this particle is at the top there. Right, let's just refer to the spring. There's your force against extension, Hooke's law. This is an unstretched spring. When you put the object down, it will be stretched. And then you pull it down further, a displacement of y. Right? F and P are elastic force from the spring. W is the weight of the object. At rest position, there's no resultant force. Right? This is called a rest position, where it's not oscillating, it's at rest. That's why it's called at rest position, no resultant force. So the forces acting will be the weight pulling it downwards, and then the elastic force by the spring itself pulling it upwards. So the two balance out. So there's your distance x. We can show it in the graph there. There's your distance x. Right? It's stretched. Then we pull it further. The weight is still the same, but we have increased the elastic force of the spring, which is F. We can show in the diagram there. Previously is P, X is P. Now your X value is less than your Y value. So that is your F. Right? The force is increased. And that is your Y. So your F is greater than your W. When the object is pulled a small distance Y, the resultant force is F minus W upwards. Right? So this time F is greater than W. So the resultant force is F minus W. And it's going to go upwards there. Okay, unstretched spring, put the object there. It come to rest as rest position. We call it rest position or equilibrium position. It's the position where the particle is not oscillating. Where there's no force, it's stay there at rest. Okay, so when we pull it down by a amplitude, why not? Call it why not? Amplitude or displace it by why not? So this is going to go up and down. Right? We take upwards that as 0, the rest position as 0, and then upward as positive, downward as negative. Upwards as positive, downwards as negative. Then you release it. Why not? It's the maximum displacement called the amplitude. So you are the one who determine it. You stretch it longer, amplitude larger. You stretch shorter, amplitude smaller. When the object is displaced by y naught, it oscillates to the rest position, then to y position, and continue to and fro. So it's going to go up and down. Right? That's called simple harmonic motion or oscillation. Same. Or we call it vibration. Same thing, same diagram. Right? We displace it downwards there. Going to move upwards. When displaced to y naught and release, remember there is a maximum force acting, maximum resultant force acting at this point there. But the velocity is 0. The resultant force is the one that gives it the velocity. So at maximum amplitude, velocity is 0. Object has a maximum upward velocity. So velocity is 0. Remember, it's acting on by a resultant force. So at the rest position, there's no resultant force, as we said before. So the velocity must be maximum. No force acting already. They must be maximum. That's where the weight is balanced by the elastic force of the spring. Right? Object has maximum upward velocity, and because it has a mass or inertia, it will continue to move upwards there. But velocity will decrease. Right? It will go up, velocity will decrease to 0. We know it's 0 because it doesn't go further anyway. Then after that, the weight is the one that's greater than the elastic force. So it's going to pull it down. Electric force is minimum. Resultant force is W minus F because W is not greater than F. Any comment? Anything not clear? So that's how the different stages are. You will go from maximum point, you go down to rest position and go down again and then go up and down. So in terms of graph, it is just oscillating to and fro that way. That's all.
Sure.
So we see horizontally as motion that way. Or we can consider the oscillation of this mass connected to the spring, and then we have a screen where we can put a pointer at the bottom of the mass where you can draw the picture on the screen there. Then we can let the paper or the screen move with constant speed. That will give us a time now. So that's why we can see that it is a waveform, sinusoidal waveform. This direction of vibration, horizontal motion of the screen. Displacement time graph. Just review your displacement time graph. velocity is obtained from the gradient. Right, in this case, it's a straight line graph. So displacement increases at a steady rate. We call uniform velocity. Right? Velocity equals to gradient. So in this case, is we take this triangle to find the gradient. So it's 50 minus 20, 5 minus 2. So it's 10 meter s minus 1. Displacement time graph of an oscillating particle upwards from the rest position. Right? There's the rest position. There's the zero line. There's a period. We will define the term later on. And then there's a twice the period. So at this case there, displacement downwards we take as negative. At this point, the velocity is 0. Right? It doesn't move further down anymore. That's why the velocity must be 0. Or we take the gradient now. Gradient is horizontal at this point. So velocity is 0. Displacement is 0. Right? At this point, at the period there, it returned to the rest position. So the displacement is 0. Velocity is maximum. Right? We take the gradient now. Positive gradient. Right? Slope gradient maximum here at this slope there. And as you go further, the slope becomes smaller and smaller. So we can draw the velocity time graph. Right? That's the velocity time graph. Right? There's a point that we're interested in. 0. That's a 0. And then at the period there is maximum. Period there is maximum. Okay, so the sine graph becomes a cos graph. Any comment or anything not clear?
Yeah, clear.
You must be able to read the graph lah. Okay, we are going to finish in 10 minutes time. So I expect you to try, since your teacher has teach you, to try the worksheet lah. Try the worksheet. Right? Velocity is maximum. Same, velocity time graph, horizontal. So acceleration is 0 there. Whereas acceleration is maximum here. Right? So where the displacement is minimum, right? Whereas the displacement is downwards. We look at the thing there. The velocity is 0. Right? And then the acceleration is maximum. Right? Positive. This is negative. This is positive. Right? Where the velocity can see from
So why when velocity is 0, acceleration is maximum?
look from the graph. Look at the gradient. The gradient is maximum here. You must learn to interpret from the graph. The gradient of the velocity time graph is the acceleration.
Uh-huh.
You must know how to
Okay.
apply your knowledge from kinematics. Anything still not clear?
Yeah, okay.
If you are interested to explore, you can go to this website to look at some of the things there. Okay, we are introducing some of the terms. We can represent progressive wave with displacement distance graph or displacement time graph. Two things: displacement distance graph or displacement time graph. Right? The picture is a displacement distance graph. Displacement distance graph is an instant photograph of the traveling wave. That means we take a picture of the wave as it travels forward. Right? So it's a frozen picture of the wave. Shows how the displacement of each particle of the wave varies with distance of the wave. It's called the crest, the maximum point. Right? This is the undisturbed position. The water, right? Think of it as this is the medium. It can be water. The undisturbed position, the surface there has a wave pass through. That's why we see the wave. And then we can call a starting point. Right? Starting point here. Distance. You can choose our starting point more for our convenience. And that is your wavelength. Right? Displacement distance graph. From crest to crest is a wavelength. And the bottom there, minimum point of the wave is called the trough. And the largest point is called the amplitude. Largest displacement is called the amplitude. Sometimes we use Y naught if the oscillation is the Y direction, or we use A for amplitude. Right? This is just displacement, no amplitude. Trough is the minimum point of the wave. Wavelength is the distance between successive crests or particles that are in phase, crest to crest, or it can be trough to trough, or it can also be from here, the zero to the same zero there. Okay, where it start again. Amplitude is the maximum displacement. This is the maximum displacement. Which of the following is a wavelength from this picture? What's it?
Wavelength.
Say again. ABI, which is their wavelength?
Wavelength should be A.
No,
A?
same point. Same point here is going up. Here is going down. Here is going down. Successive one.
Teacher, I thought both also can.
Cannot. B
Wait,
is,
no.
A is more than a wavelength.
Oh, yeah.
From
Yes, sorry, I
here
saw
to here
wrongly.
is one wavelength. So it's more than a wavelength. I is how
Yeah.
many wavelength?
Wait, I count. Oh, I is like
Two
2.
wavelength. No?
Oh,
Right? From crest to crest is one wavelength. From crest to crest, another wavelength. So it's two wavelengths. Right? Then you have the displacement distance graph. Sorry, displacement time graph. So H is called the period. Displacement time graph. Right? Will be cut off at any time now. Shows the displacement of particle with time as the wave pass through. Right? We're looking at a particular particle for displacement time graph. So as the wave pass through, the particle is oscillating up and down, or we call it simple harmonic motion, to and fro. And same amplitude maximum displacement from the rest position. Frequency is the number of wave crests passing a given position each second. So we count the number of crests passing a particular position, and that's a frequency in unit time. Unit is hertz or per second. Same. So period is the time between one wave crest and the next arriving at a particular point. Unit is second. That is a period from crest to crest. This is the displacement time graph. And period equals to 1 over frequency. Wave speed, what is monochromatic light? Any idea? What is monochromatic light?
single wavelength.
Good. Single wavelength, correct. Monochromatic light is a light of a single color or single wavelength. What is the wave speed?
Speed of light, right? It's equal to the speed of light.
No. Wave speed is the distance traveled by the wave per unit time. Right? We can look at the crust,
definition.
how the crust move in unit time. Okay? General definition, not the speed of light. Unless it's light, then it's speed of light. So V equals to F lambda. Right? Derivation, you must know how to derive. Since the time taken for a wave crust to travel a distance lambda is t is a period, or 1 over f. The velocity of wave, right? Velocity is x divided by time. Distance divided by time. So distance is lambda, time is period, so it's lambda over period, or 1 over t is, right, frequency, so f lambda. Need to memorize that. Phase and phase difference. Phase of an oscillating particle. Phase of an oscillating particle is a measure of what fraction of a cycle the particle has completed as measured from a chosen starting point. Usually identified as a phase angle. Example, the particle at A is 90 degrees and the phase difference between particle A and B is 180 degrees. And we take the rest position as your starting point, 0. So it basically helps us to identify in a cycle where's the particle. If it's at the topmost, 90 degrees. Right? So it's basically like a sine wave. So as I said, anytime we cut off, right, 180 will be down there again. So it's oscillating up and down. Right? So you can think of it as a sine curve. Right? We'll carry on from here. Anything you want to ask before it cut off?
No.